Today we're going to discuss radioactivity and how we represent radioactive processes in nuclear equations. So when we have a nucleus, keep in mind that the nucleus of the atom is very dense. Roughly, it is about 2.4 times 10 to the 14th grams per cubic centimeter. Well, what does that mean? It means that if we had a nucleus the size of a marble, look at how much it would weigh. 250 million tons would be the mass of that little bitty marble. So you can see that it's incredibly dense. We have learned in previous discussions that the nuclei contains protons and neutrons. Now, there are lots of other particles that have been discovered, which many are thought to be involved in holding the nucleus together. Remember, that's a problem because we have positive protons in the nucleus and they are attempting to repel from each other. So something strong must be in there holding that nucleus together. We sometimes call it the strong force or binding energy. Now, some atoms don't have enough binding energy, and if they don't, they become unstable. And in an effort to reach a more stable state, these atoms will emit particles or waves of energy, and those particles and waves of energy that they emit are known as radiation. And you can look up the history of the discovery of radioactivity. It's very fascinating with individuals like Henri Becquerel and Marie and Pierre Curie. But moving on with the discussion of what this is, when we have these high energy particles or waves that are being emitted from a material, we call this radioactivity. Now, if the particles change, this emission of the particles change the identity of the atom, we call it radioactive decay or transmutation. And unlike chemical and physical processes, this nuclear process does actually result in the formation of different atoms with different identities. The emission of waves of energy, if it's just waves of energy, it does not change the identity, and we'll see how that plays out in just a moment. But before we do that, let's just real briefly just have a review over how we represent these particles, because isotopes, we have to take into account that they're going to be the same element. They're atoms of the same element. They have the same number of protons, obviously, the identifying particle, but they do have different numbers of neutrons. And radioactive isotopes, often called radioisotopes, are isotopes of atoms that are unstable and emit radiation. So just a quick review. Remember, if we have this symbol, the X in the symbol stands for the element that we're dealing with. The number on top is the mass number. Remember, that's the protons plus the neutrons. The number on bottom is just the protons. That's the atomic number. So if we wanted to represent an isotope of cobalt that has 33 neutrons, first of all, we'd write down CO for the cobalt. Keep in mind that that 33 is never going to appear on the symbol anywhere because the top number is the protons plus the neutrons, and the bottom number is just the protons. We'll need to use it, it just won't be part of the symbol. So the bottom number, we look cobalt up on our periodic charts, we see it's number 27, which tells us that it has 27 protons. Now we need that 33 because we need protons, 27, plus neutrons, 33, and we get 60 for a mass number, and that's what our top number is going to be. Also remember that we can write the name of this isotope by simply writing cobalt and putting that top number, that mass number at the end. So cobalt 60 is the name of this isotope. So what kinds of radiation do we have? There are all different kinds, and we'll learn more of them if you take AP, but we're going to emphasize three different types of radiation right now. The first is the alpha particle. It has the symbol alpha. It's written like this, and it's handwritten. It's a positively charged helium nucleus. So what we have is just a nucleus that has two protons and two neutrons. It's positively charged because it doesn't have any electrons. So that's our alpha particle. It's quite big. It's like the 18-wheeler of the radioactive world. So it's not going to be able to get through a lot of materials. Even paper or skin will stop it. This is the symbol, 4/2He. And how would we represent this in an equation? Very large elements, and we're going to use californium for this one, very large elements above bismuth are unstable and tend to undergo alpha decay when they're that big. So look at what this does. And you can see it written out in the yellow portions here. The daughter nuclide is the element that's formed, and then of course we have the radioactive particle, the particle that's being spit out of the nucleus, alpha particle in this case. And notice something else. The top number, or top numbers as the case may be, must be equal on both sides of that equation. Same way with the bottom numbers. If we have this 98 on the left, then the 96 and the 2 on the right had better add up to 98, which of course they do. So that's how we're going to be able to complete nuclear reactions. So look at this example. We've got platinum, 190, and we're wanting to see what the daughter nuclide would be if it spits out an alpha particle over here. So if the top number here is 4, the top number here is 190, then 186 on top for this particular isotope, the daughter nuclide. If there's a 78 on the left, remember this has to be equal on each side, and there's already a 2 over here on the right, then evidently the bottom number must be 76. So how do we find the isotope? Or excuse me, the identity of the element? It's that bottom number, remember, that we look up on the chart. And if we look up number 76, we see that that is osmium on our periodic table. So that's how we complete a nuclear reaction. The second particle that we need to be familiar with is the beta, and the beta looks like kind of a cursive B with a tail when you handwrite it. It's negatively charged because it's simply an electron. It has moderate penetrating ability because it's quite small. Even wood will stop it. Skin and paper won't, but wood will. It has this symbol. It has no protons and no neutrons, so it's got a 0 for a top value. Of course, it has no protons, but the bottom number, the -1, indicates the charge. And it also helps us keep track of what's happening to particles in the nucleus. Look at this example here. We have, notice that a beta particle being spit out does not change the top number. It does, however, change the identity because that bottom number being a -1, keep in mind it's a -1. Be careful. We've got this 26 here minus the 1 is going to give us the 25 on the other side. So let's fill this in. We have 161 over 65 on the left, 0 over -1 on the right. So once again, the top number is not going to change. The bottom number, however, will. Be careful. Lots of people put 64 on the bottom. No, if you put 64 on a bottom, 64 minus that 1 for the beta particle would be 63. And that would be getting further and further away from the 65 over here on the left. So keep in mind, to keep this equal, this bottom number here would need to be a 66. 66 minus 1 is going to give us that 65 we need to match up. Now, what is the element? Look up number 66, and it's dysprosium, dy. So that's that particular reaction completed. The last type is gamma. Gamma looks like, keep having people write it looking like a Y. Looks kind of like a nose-diving fish, actually handwritten. Gamma radiation is chargeless. It has 0 charge. It's not a particle. It is simply radiation. It's energy. That's it. It's not a particle. Since it's not a particle, it's just electromagnetic energy, it's not going to change the identity of the element that's giving it off at all, because its symbol is 0 over 0 gamma. So let's look here. Looking at what type of radiation is being emitted and completing the reaction. Keep in mind that all of these arrows should be equals. 0 on top, because that top number did not change. The bottom number better be a -1. 94 minus that 1 is going to give us the 93 on the other side. What particle is this? It's our beta particle. So this is beta decay. It did change the identity. In the next one, look at our two nuclei, our two nuclides. No change in identity. So we've got 0 on top, 0 on bottom for this particle. The only particle that matches that is our gamma particle. So this is going to be gamma radiation given off by this particular radioactive element. Finally, on the last one, we've got 220 on the left, 216 on the right. We need another 4 on top. To match the 86 on the left, our 84 needs a 2 added to it. And the particle that matches those numbers is our 4 over 2He, which is our alpha particle. So this is going to be alpha decay.